All right. How's everybody today? Great. Good to hear it. We have our next focus activity. We'll get to that in just a minute. They will be due next week, Wednesday. I believe that is the 3rd of April is when I'll officially be looking for those. We'll have the fourth one probably Monday or Tuesday. I haven't decided which yet, but we will have 4 in the set, so we're not going to turn them in just yet. That's going to be one of our last grades. What's happening tomorrow? Got a test. Now, it's just over the trig equations. Okay. Most of it's going to be multiple choice. There are going to be a few open-ended. I believe I also did provide a unit circle on the exam. So you're allowed to use your notes anyway, but you also have that if need be. So I don't believe it's going to be a problem. You guys have been responding really well to trig equations, so I think hopefully it'll turn out good. Then, next week we'll continue with vectors, what we're doing today, and district assessment, and Friday is going to be the end of the 6 weeks. Next Friday, that is. Okay. Well, let's get to it. This is the third focus activity. Now, this is something we haven't seen for quite a while. It does go back to, I believe, it is in the first semester. Determine the value of x. So does anybody know what could possibly help me find this angle measure right here? Okay. Well, no, the two triangles are separate. Okay. It is an equation. In fact, it's a law. Now, law of sines or law of cosines? Now, why can't I use law of sines?
Because it doesn't have the co in front of it.
It doesn't have the what?
The co in front of it.
The co? Okay. There you go. That's exactly right. We need what's called a pair. See, in order to use the law of sines, like in, say, B, I need an angle measure and the side length directly opposite from that. So in B, I can go ahead and use the law of sines. But for A, I'm going to have to use the law of cosines. Now, remember, the form followed this. And it doesn't matter, if your triangle is labeled ABC or whatever, but we had A squared is equal to B squared plus C squared minus 2BC times the cosine of angle A. Remember, the uppercase letter was the angle measure. The lowercase was the side length. So I'm looking for X. So how am I going to start my equation? Could be anything. I mean, let's go ahead and say that, this is angle A right here. And then, it doesn't matter. This could be B and this could be C. So I would start 11 squared.
19 squared plus 13 squared minus 2 times 19.
Okay. Times cosine of X or cosine of A, whatever you want to call it, as long as we know we're referring to that one angle. Okay. Yes, remember the pattern always stayed the same. Whatever side I started the equation with, we take the other two sides, we square them, we add them, then minus 2 times their product, and then times the cosine of the angle across from the side I began the equation with. So if I started with side B, remember I would end with angle B, and so on. Okay, well the goal is I want to get that cosine of x by itself. I wanted to read cosine of x equals. So the way we did this, remember we did it in parts. Okay, so I'm going to first subtract both of these terms over. So this would be 11 squared minus 19 squared minus 13 squared is equal to negative 2 times 19 times 13 times the cosine of x. Okay, all I did was subtract both of those terms over. Okay. Well, what do I do now to get cosine by itself?
You divide, you add.
No, you're right. Divide by what? In fact, divide by that product there. So I'm going to divide by the negative 2, the 19, and the 13. Do the same thing over here. I don't need parentheses on that one. Negative 2, 19, 13. Because see, those negative 2's cancel, 19's cancel, 13's cancel. So now I've got cosine of x equals this. Okay, so let's go ahead and see what that value is going to come out to be. So I come on over here. Let me get rid of that. So control divide. We start at 11 squared minus 19 squared minus 13 squared. Then we're going to divide that by parentheses -2 times 19 times 13. Okay. So when I push enter, this is what I'm getting. 409, 494. Okay. 409, 494. So you can put the decimal value of that if you want to. So 409, 494. Now remember, we're looking for an angle measure, but I have the ratio. Does anybody remember what I need to do to cosine? I need to take his inverse. Remember, I'm going to switch these. If I evaluate cosine at an angle, I'm going to get a ratio of the sides. So I'm going to evaluate cosine inverse using the side angles, and that's going to give me the x value I'm looking for. Okay, so let's see what that turns out to be. So I'm going to come on over here, trig cosine equals, okay, I'm just going to go ahead and, went a little too far. It will not let me do that, so here we go. There we go. Copy that. Just go ahead and put that right in there. And as soon as I push cosine inverse of that ratio, looks like I'm getting about 34.1 degrees. Okay, there we go. Okay, so about 34.1 degrees. There we go. Perfect, perfect, perfect. Okay. This is not on the test. I just thought it was a good idea to go ahead and kind of spiral it back in just to show it to you. Since we're not going to have a whole lot of use for it later on, it could potentially show up on the final though. So I'll just keep you up to date with it. So let's take a look at B. Now I did mention that on this one we can use law of sines. Okay, we do have what's known as a pair. Now remember, the law of sines was just the sine of angle A over side A equals the sine of angle B over side B, which is equal to the sine of angle C over side C. So all you're doing here is setting up a proportion. Okay, now, am I looking for an angle measure here or a side length? Side length, so I'm not going to need to use sine inverse. Okay, so that's not a problem. So let's start with that pair I referred to. Let's say sine of 40 degrees over 17 equals. Now we're looking for x, so I need to go ahead and say sine of 72 over the x kilometers. Okay. And how do I solve a proportion? Cross multiply. That's exactly right. So let's see here. X times sine of 40 is going to equal 17 times the sine of 72 degrees. To solve for x, we'll divide through by sine of 40. Okay. Anything divided by itself is 1, even a trig function. And now the length is just going to be whatever that ratio turns out to be. 17 sine of 72, let's see here. Okay, control divide, 17, nope, I got to hold, let me get out of here real fast. Delete. Okay, so 17 sine of 72, and then I believe we are going by sine of 40, right? Okay, sine of 40. All right, so how many kilometers is that side length going to be? I'm waiting for someone to tell me this before I push it. Like I'm doing the, Okay, well, looks like we're getting about 25.2. Is that what you guys are getting? There we go. 25.2. All right. Okay, perfect. Any questions? Did anybody happen to have that completed before we started? No? Did anybody remember law of sines, law of cosines? Okay, but just now, see, there you go. That's why we're doing it. Okay, so put this someplace safe. You now have 3 focus activities. There are still a few extra over in the folders by Christian if you've lost or misplaced one. We're turning them in next week. We'll have 4 total. Okay, we're going to record that as a quiz grade. Okay. All right, so let me take care of that. So you want to save changes? Sure. Okay, now, moving on. Okay. If you'll go ahead and take out the notes from yesterday, or if you don't have them, they are over in the filing cabinet. Well, I'm going to say filing cabinet, but filing system over there. Okay, so we started talking yesterday about vectors, and we started to look at what we can do with them. We haven't gotten into any really applications yet. We're still looking at just the basic skills. Okay. Let's see here. There we go. All right. So a vector, the example we saw yesterday from Despicable Me is actually a correct math definition. Okay, it's a math quantity represented by an arrow that has both what? Direction and magnitude. Oh yeah. Okay. Then you pull out a prana gun and there you go. Okay. All right. But what we started talking about yesterday, the magnitude could be a variety of things. It could be the length of the arrow itself. We're talking distance. It could be force. You know, like I said, we're going to do a little bit of physics, but not a lot because this is not a physics classroom. Or it could even be the speed of an object, and that's just to name a few. That's typically what we're going to be looking at in here. So the double bars represented magnitude. That was our notation. Lowercase bolded letters. Okay. Now, there's two parts to a vector. We have the tail that we call the initial point, and then we have the head, which is the arrow. We call that the terminal. Now, if the initial point is at the origin, what do we call that? Standard position. That's really, really important. So every time we know of a vector in standard position, that means it starts at the origin and then just goes off in whatever direction it wants to. Okay. And then we did some scalars here. We multiplied and shrunk it. If you multiply by a negative, that changes the exact direction that the vector is going. And then we did some problems here. If you're given a couple of points, an initial and a terminal, and you wanted to know the component form, you always start with what point? Initial or terminal? Terminal. Always start with the terminal and subtract the initial. That is exactly right. Now remember, component form was going to look like this. It was going to look and act just like an ordered pair. A is your horizontal movement. B is your vertical movement. Okay, but we know that we're dealing with a vector because instead of the parentheses, we have these arrows on either end. Now, if you're asked to find the magnitude, the formula that we want to use was going to be the square root of a squared plus b squared. Okay. Remember that component form was going to tell me a set of instructions how to move horizontally and vertically from the initial to the terminal. And then we did several examples, and I went ahead and gave you some of these right here. Okay, so let's see what else we have. Now, vector addition. All right, when adding two vectors, we draw them using the tip-to-tail method. The sum u plus v is called the resultant vector. Every time we get an answer when we do something with a vector, we call it the resultant. That's why a lot of times when we're working, we'll just use r for that answer. To geometrically represent the resultant, you want the initial point or tail of one vector to coincide with the terminal point or head of the other vector. The magnitude and direction of the vectors must not change. Okay, the resultant is the vector that points from the tip of u to the tip of v. Okay, now I'm going to go ahead and introduce this to you. I'm going to show you how you would do this graphically, but we're not going to be dependent on it. We're going to go ahead and do things algebraically. But I do want you to get an idea how this works. Yes, Lexi? Yes, you can add and subtract vectors. In fact, you'll notice, let me go ahead and show you this right here. Okay. I've gotten copies of these two vectors right here. So this is vector A, this is vector B, and you'll notice for each one I've got a segment of the same length going in the same direction, okay, to help us out here. But just so we can kind of remember component form, okay, let's say this A right here, let's say that initial point is the origin. So what would the component form of A be? Okay. How far horizontally and then vertically do I have to move? There you go. I've got to move right 3 and then up 4. So A would be 3, 4. Remember, that's component form. Okay. Now, when would one of those values be negative? If I moved what two directions?
Down or left?
If I moved left or down. That's exactly right. Now this one here, B, let's pretend that this point right here that I highlighted, that's the origin. Well, what would this one's component form be? There you go. How do I get from the initial to the terminal? All I did was have to move 4 to the right, and I didn't move vertically. So B would be 4, 0. Okay. All right. Now, I want to go ahead and show you how we can start adding and subtracting vectors graphically. Like I said, we're going to focus more on this algebraically, but I just want you to go ahead and get the idea, before you take off today. The only catch is that when you position these vectors, you're trying to create a triangle. We're calling that the triangle method. But you have to put the end of one vector to the tail of another. So it has to be initial to terminal. You can't put two initials together, and you can't put two terminals together. When you connect the two sides, it has to be initial and a terminal. And it actually doesn't matter how you do it. Let me go ahead and move one of these out here. So let's say I take A. I'm going to take vector A. All right. I'm going to put it right here. And see, no matter where you put it in your plane, the component form is always the same, because don't I have to go 3 to the right and then 4 up? See, the magnitude, its length, and the direction is not changing. Okay, but right here, this is the terminal end, right? So what I want to go ahead and do is take B now, and I want to place it in such a way where I'm starting to form a triangle. But can I put those two together? No, I can't put two terminals together. I can't put two initials together. So I need to go ahead and put the tail end of this vector with the head of that one. Okay, right there. So this would be, this is vector A. This is vector B. So now what I'm going to go ahead and do, this creates two sides of a triangle, right? This is why we refer to it as the triangle method. If I now go ahead and connect this to this, if I create the third side of the triangle, that resulting vector is A plus B. Vector A plus vector B. So let me go ahead and get a deal right here. So if I connect this to here, this third side, this is now A plus B. There we go. That's exactly right.
So,
Okay.
the whole head and tail rule,
Uh-huh.
does it only apply to adding or subtracting as well?
It applies to subtracting as well. Even with subtracting, you can't put two terminals together, cannot put two initials together, and it has to be initial and a terminal. I'm sorry? Kind of. Think of it that way, yeah. Now, you'll notice I put the terminal of A to the initial of B, right? Okay. I want to go ahead and show you something. Let's go ahead and do this again. Let me put A out here. Okay. Well, let's connect these differently. You'll notice instead of putting A's terminal to B's initial, why don't we reverse it? Why don't I put B's terminal to A's initial? So it's actually going to look like this, right? Okay. So this right here is B. That's his terminal. This is A. So it does not matter how you combine them. If I can finish up the third side of the triangle now, that should be represented as A plus B. You're going to get the same answer every time. Now, check this out. Okay. Let's figure out the component form of A plus B. Okay. So I want to go from here to here. So how far horizontally do I have to go? How far right? Looks like I went 7 right, and then how far up? Looks like 4 up. Now, if both of these are actually going to give me the same answer, then this A plus B vector should give me the exact same component form. Well, let's see. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Okay. So see, it does not matter how you combine the two sides, as long as it's an initial to a terminal. You'll always end up with the right answer. Okay. Does that make sense? Okay. All right. Well, let's try another one. Now I want to show a plus b. Now, when you have subtraction, don't think of it as subtracting a value. Think of a minus b as a plus negative b. Okay, so let me go ahead and take off these other ones here, because I'm going to continue to use these. So I don't need this one. Don't need that one. Okay. Let's go ahead and move these guys back over. Okay, now here's the thing. I'm going to take a plus negative b. So let's say this is a right here. Okay, let's go ahead and say that's a. Well, think about what we did yesterday. What's going to happen if I make b negative? It changes one thing about him. It changes his direction. So if I suddenly go ahead and make b negative, that's the initial, that's going to be the terminal. So I want to go ahead and use b, but now he's going in the opposite direction. And when I connect these, all I have to make sure of is that an initial touches a terminal. Does not matter how I do it. Okay. So I'm going to go ahead and move this guy over. In fact, because he's already pointing in the opposite direction, why don't I go ahead and put this guy right here? Okay, so this is vector A. This is the opposite of B. Remember, all we did was change his direction. See, we have an initial to a terminal. So how in the world am I going to figure out, whoop, no, not that one, what the A minus B vector is going to look like? What kind of figure am I trying to finish up here? Triangle. So I just create the third side of the triangle right here. Now, whatever side you're subtracting, okay, the terminal end goes there. Now, when you create the third side of your triangle, you're most likely going to have two initials together and two terminals together. That's perfectly fine. But when you put the first two sides together, it has to be an initial with a terminal. So this right here would be A minus B. Okay. Does anybody have any questions about how we're doing this? Okay. And we call it the triangle method because we are creating triangles. There's also another method that you may see for those of you who move forward in mathematics. It's called the parallelogram method. It's just as nice, but I just think the triangle is so much simpler, faster. You don't have to worry about the parallelogram. But there is another method that exists. Okay, let's try this last one here. I want 2a plus b. So what do you think is the first thing I'm going to do here? There you go. First thing I'm going to do is double A. So you'll notice that's why I've actually got two A's to begin with. Okay, so here's one A right here. Whoop, don't need that. Here's one A right here. So let's say I put A right there. Okay. So now if I take another vector A and just put them end to end, what do you think that would be? That's 2a. Now, we're not multiplying it by a -2, so what does not change? The direction. So it's still pointing up and to the right. So now I want to take this vector and I want to add it to B. Okay, so I'm going to come back over here. So now B is going to be pointing to the right. Well, you'll notice I could just go ahead and connect it. I could take the initial and put it to the terminal right there. Just like that. Okay, so here's B. He's pointing to the right. Okay. So how am I going to find the vector that represents 2a plus b? Yeah, just make the triangle. Here we go. So I'm going to connect here to here. Okay. So there you go. This would be 2a plus b. There you go. Like I said, there's a lot to be said for doing it graphically, and some people like to do all their problems graphically, but I'm thinking the easier way, just so that everybody's on the same page, we'll just use the algebra. Okay. Any questions about this? No? Okay. Well, speaking of the algebra, let's take a look. V has a component form of AB. W has a component form of CD. Well, In order to add two vectors, you just add the A and C, the x values, and you add B and D, the y values. Okay, basically just the corresponding values, you're going to perform that operation. If you want to subtract them, you'll subtract the corresponding values, get that new one vector. Now, k is just a scalar, so if you have k times a vector, it's just like distribution for a vector. You just multiply across. Yeah. Now, if you multiply two vectors, you're going to get a scalar, but that's coming up in the next lesson. Okay. So if you just multiply a number times a vector, it's still going to be a vector. All right. So let's try this one here. A says negative 3u. Well, it's giving me that u is negative 3.8, and we know that v is 5.2, right? So when it says negative 3u, well, all I want to do is take negative 3 and multiply it by negative 3.8. Okay. So when you have a scale factor out in front, well, you're just going to distribute. What is negative 3 times negative 3? 9. So that would be 9. Negative 3 times 8? Oh. Negative 24. There you go. That's it. Okay. Just like that. Let's try the next one. 2u minus 3v. So before we can take the whole problem, we have to take the terms individually. So I want to multiply 2 times u, which is negative 3.8. And then I want to subtract 3 times v, which is 5.2. Okay. Now, let's go ahead and distribute here. So what do I get if I double u? Okay, so negative 6, 16. And now what we're going to do, if this term here, if you're subtracting, we're going to go ahead and distribute the negative with it. So that's just going to leave me a plus because we're taking the negative. So what's negative 3 times 5? Negative 15. Negative 3 times 2? Negative 6. And then now, well, how am I going to add two vectors together? How do I do that? There you go. The negative 6 corresponds to the negative 15, right? What does the 16 correspond to? That other negative 6. Almost, yeah. It's just a way of organizing the information. So what is negative 6 plus negative 15? Negative 21. And then 16 minus 6? What? Okay, 10. There you go. There you go. That's it. Any questions? Okay. Now you'll notice this one here, it has 2u minus 3v, but that's what we just solved, right? Oh, so it's not absolute value. What's the double bars? Starts with an M. That's the magnitude. Okay, so remember when you see the magnitude, what you want to do is take the square root of a squared plus b squared. So we're trying to find the magnitude of this component form, negative 21, 10. Well, what represents A? Yeah, negative 21. So there's your A. What do you think B is? There you go. So I just want to take these values, A and B, the horizontal and the vertical, I just want to plug them in that formula. So the square root of A squared, well, that would be negative 21 squared, plus B squared, 10 squared. Okay. And then we just go to the calculator to figure out what that is. Okay. So let's see here. Get rid of all of this, document B. So the square root of parentheses negative 21 squared plus, I'm just going to go ahead and put 100 because that's 10 squared. Okay, so A squared plus B squared below a radical. I'm getting like 23.3. Okay. So here the magnitude, the length of that resulting vector should be 23.3 units. Okay. All right. How are we doing? Any questions? No? You guys want to try one on your own?
Yeah.
Okay, so try D. And then we can go ahead and confer with our partners, our villain buddies around us, see if we're getting the same answer. So remember, you want to evaluate U minus V first, then take the magnitude of that resulting component form. Okay, so I'll catch up to you guys in just a second. Remember, is any of this on the test tomorrow? No, 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 no. Okay. This is not on the test. It's just the trig equations. Oh, and everybody who needed the key for yesterday's homework, did everybody get it? Anybody need that? You got it? Okay. Nobody else need it? Okay. Well, I'm not going to go ahead and work the problem just yet. I'm just going to go ahead and get it set up. So the first thing I need is U minus V. So U is a negative 3/8. And then I want to subtract 5/2. Okay. Well, let me go ahead and catch up to you. You may not be done, and that's okay. But what would negative 3 correspond to if I wanted to add or subtract it to another vector? Okay, 5. There we go. And then 8 would go with the 2 right there. So just subtract them. What's negative 3 minus 5? Okay, that's a negative 8. 8 minus 2? 6. Now, if we simply wanted U minus V, we'd be done. The problem would be over. But remember, we want the magnitude of that now. So in this component form, that's my A, that's my B. Okay, and what's that formula that we've seen several times now? A squared plus B squared below that radical. Made that a little longer than I needed to, but that's okay. So the square root, that would be A squared negative 8 squared plus B squared 6 squared. So that's the square root of 100. So this one actually works out nicely. The square root of 10 is 10. So whatever U minus V looks like, its length would be 10 units long. That's our magnitude in this case. So it has direction and magnitude. Okay, good. Good, 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 good. All right. Questions? Okay. All right. Well, let me go ahead and kind of demonstrate an example for you. Okay. Let's say we have this one right here. Okay. Now, I've already got U and V positioned so that the terminal of one is touching the initial of another. And this isn't in your notes, and that's okay. Okay. But somebody help me out here. I want to know the component form for U. So let's see, how far, I know it's kind of hard to see, but how far did I have to go, right? 15, and then how far up? Looked like 6. So U's component form would be 15, 6, right? Okay. Now let's go ahead and do the same thing for V. All right. And it doesn't matter where it is. I want to go from here, the initial, to the terminal down here. So how far down did I go? Do the little dot thing? Yep. Some people are noticing it, so 16, there we go. But it would be what? Oh, negative because we went down, right? Oh, yeah, it would be B. I was just saying if you're paying attention, obviously you were. You got to throw those at you every now and then, you know. Okay. Because remember, you always move horizontally first. So we know we got to go down, but how far right do I need to go? 5, 6. Okay. All right. Well, now let's say I wanted to go ahead and find u plus v. Okay. So it would be 15 plus 6, which would give me what? 21. And then that would be negative 10. 6 plus negative 16 is a negative 10, right? So you remember what I said a second ago? If we're going to do it graphically, we have our two vectors, one terminal to an initial. We create what figure? The triangle. So let me go ahead and show you this real fast, because I want you to make a connection with what we were just doing. If I now go ahead and finish up the third side of this triangle right here, connect it right there. Okay. Here's where the terminal would be. This should represent u plus v, right? Now let's check it with the answer we got. Let me go ahead and erase these right here. Okay, those right there. So I should be able to go from this right here, right how far? 21, and then how far down? 10 to get to the terminal point right there. Let's see if it matches up. So bear with me for 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21.
Yeah.
So I went 21 right,
Yeah.
and now let's see if I go 10 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So does what we got algebraically match up with what we did graphically?
Yeah.
Yes. So I just want you to see that no matter if you do it graphically or if you do it algebraically, you're always going to get the same answer. Okay? But we're going to be focusing on this. We're not going to be doing a whole lot more graphing as far as the word problems go. Okay? All right. What do you guys think? How are we doing with vectors?
Great.
Is it great? Okay. All right. Well, that's all we got.